Next reaction that I wanted to talk about would be a nitration reaction. These are all electrophilic aromatic substitution reactions. And just like with the other one, well, I'll go ahead and draw the overall mechanism, the general reaction here, the overall reaction, which starts off with a benzene ring. I'm just going to draw benzene rings like that. I know, I'm horrible. It's a hydrogen there. We go ahead and react this with HNO3 and H2SO4, and what we get out of this is a nitro group attached to it. Now, nitro groups are pretty useless. They don't react if you take a drug that has a nitro group attached to it, it's going to be very toxic to you. But if you go ahead and treat that with, say, palladium on carbon and H2, I only draw solvents down there, so I'm not going to put that in there. You can convert that to a NH2 group, which is really nice to have for these type of reactions. So that's the general reaction for nitration. Let's kind of go into the individual steps. So I'm going to go ahead and draw these two kind of branching off from here. Hopefully I will not run out of room. So step one is to create a badass leaving group / electrophile. So how do we do this? Well, what are our reagents? HNO3 and H2SO4. And I'm just going to go ahead and label this thing here, and then we'll talk about the second step next. But the second step after we create that badass leaving group is the generalized substitution reaction. And I'm only going to have room for one of these, so I'm just going to draw out the creating of the leaving group first. So what we have is we have this HNO3, so it's a nitrogen there with 3 oxygens, an oxygen there and an OH there, and that oxygen has a negative formal charge, nitrogen has a positive formal charge. And we're reacting this with H2SO4. So let's draw the structure. I'll switch colors real quick too. That's our sulfur there. Kind of a goofy looking S there, but that's our sulfur. It's got this there, there. I'm not going to draw the wedges and dashes, but they're there because it's the geometry of the molecule. And 900 times out of 10, this negative charge oxygen is going to pluck a proton off of this. But I'll just make a note here that 1 out of 10 times, give or take, you're going to have a, go ahead and see if I can draw that. You're going to have a lone pair on this alcohol group, essentially an OH group, deprotonate that acid, or that acid will deprotonate at that lone pair. And so what you get from this, and go ahead and just draw the reaction going forward. I'm not going to draw the full thing, but I think you can understand that there'd be a negative charge there. I just don't have room. So we have HSO4 minus, that's our conjugate base from our acid reaction. And what we get out of this, though, is the most unstable thing, something that you're only going to draw this once. Never in a million years will you ever draw this again. So there's an N, there's an O, there's an O minus, there's a plus there. O, and that's a water group now. Okay, so we now have 2 positively charged molecules right next to each other. This is the only time that will ever happen. And so being this way that they're super unhappy about this. They're really unstable about this. So what you get is a intramolecular, well, it's not necessarily, yeah, I guess you could classify it as an intramolecular reaction where one of the lone pairs on this oxygen is going to move in, and in doing so pluck that water group off, so that what you get out of this is a weird looking thing. It's called a nitronium ion, but it's so weird looking. It's really goofy and unstable. And of course you get water as a leaving group. Who knows? I honestly don't know whether it'd be the water or the H2SO4 or the HSO4, sorry, that deprotonates it. But anyways, this is our mission accomplished. This is our electrophile. And it is a very good electrophile so that when we do that substitution reaction. So let's go ahead and draw out the substitution part of a nitration reaction. So nitration, substitution, nitration, substitution. So the first thing we have is a benzene ring. There's a hydrogen attached to that, and it's going to be coming along that the super ugly, not ugly, but just goofy ass molecule of a nitronium ion, the positive formal charge on nitrogen. We're going to come in and we're going to react with this. So I'm going to take this pi bond here, and it's going to react with that nitrogen. And in doing so, you can arbitrarily, it doesn't really matter which bond you break. I'm going to just go ahead and add that to there. But what we get out of this, orange, gold. What we get out of this is, I'm going to make sure that we draw that this is slow. Despite the fact that this is super reactive, these benzene bonds are so stable. We're disrupting aromaticity in this reaction. What we get out of this, pi bond, hydrogen there, is a carbocation. And I'm just going to draw it like, well, I guess I'll go ahead and draw the whole thing. That you have a nitro group there, O minus. And, well, I mean, a nitrogen has a positive formal charge. That's not really important. I'm just going to draw it like this, as a generic base. This could be water, or this could, I think it would be more or less like water than it would be to be the HSO4, but that doesn't really matter. But this reaction here, this deprotonation reaction, which puts that pi bond there, is restoring aromaticity, so obviously it's going to be fast. So hopefully you're seeing a pattern here between the two, or just in every reaction that we've drawn. So as we were doing this, we restore aromaticity. And I'm just going to write that as a NO2 because I don't have room to, oh, maybe I do. So that's your product for a nitration reaction. The only hard part is using that HNO3 to form this super stable, or super unstable, sorry, nitronium ion that's crazy as hell. But next reaction that I'd want to talk about is the sulfonation reaction. And I'm tired of using gold, so I'll use this. Sulfonation. This is electrophilic aromatic substitution reaction of sulfonation. And just like in the last one, I'll just go ahead and draw out the overall mechanisms. You have a benzene ring here. Just drawing it like that. You go ahead and react it, and what you get out of it, I will label my substituents in that color. We treat it with SO3 and H2SO4, and what we get as a substituent attached to it is an SO3H. So kind of messy, but just like in the last one, or in every one that we talked about, there's always two steps. The first step is to form your electrophile slash leaving group slash, I'm going to say LG. And so how do we do this? Well, we have SO3 reacting with H2SO4. So I'm just going to go ahead and draw the Lewis structures for each of those. We have SO3 there, and then H2SO4. I'll just go ahead and draw these as wedges and dashes, but OH, NOH there. So what happens with this is that the pi bond in this oxygen here is going to be, this is that strong acid that we're reacting with, it's going to be attack that proton, and then doing so the classical, you know, deprotonation reaction that you have with this. So this is going to float off in our mixture to become just HSO4 minus, which we're going to abbreviate as just A because that's the conjugate base of that acid. But what do we get out of this? Well, what we get out of this is a sulfur molecule that is really goofy looking. It's got now has a positive formal charge and an oxygen and a hydroxy group, sorry, attached to it. This right here, this is your electrophile for your reaction here. So that's the first step. The second step is just the same old of substitution. And I'll see if I can fit that on here. I'm going to switch to blue though. So we have our benzene ring. There's a hydrogen there. It's going to see this electrophile. I don't even know what the name of this electrophile is. I feel like I should know. But there's a sulfur there. Oxygen. Oxygen. OH. Positive formal charge. Whoa. Let's see if we can't clear that up. Ay, mi chada. Okay, so there's a sulfur there with a positive formal charge, and then the lone pair is going to be attracted to that. It's not so much that the lone pairs, it's not so much that the pi bond's attracted to that, so much as that that's such a strong electrophile. And this reaction is going to be very slow. Very slow. Why is it slow? Because you're disrupting aromaticity. So I'm going to go ahead and just draw these things out. Positive charge there, there's an H there, and I'm just going to go ahead and write it as an SO3 plus because I do not have room, but I should be expected to. SO3H there, and coming along is our conjugate base from our first acid reaction, and it's going to do what all bases do to protons. It's going to pluck a proton off, and in doing so we get very, very quickly, in a very, very fast reaction, is the restoration of aromaticity. Drawing the same, you get really tired of drawing these same reactions over and over and over again, just tweaking them very differently. So you have an SO3H there, and you are now done with your reaction. Cool. So that's sulfonation. Now let's talk about reactions, and specifically I'm going to say Friedel-Crafts Acetylation. This is an electrophilic aromatic substitution reaction, so I'm going to go ahead and just draw my overview of my reaction. I have this benzene ring there. I'm going to react it with something that's going to give me a substitution reaction, and my reactants of this are something with a carbonyl group and a chloride to it, an alkyl chloride, not an alkyl chloride, sorry, an acid chloride. I treat that in aluminum trichloride, and what I get attached to it is a keto group and then a carbon chain. So that's our overall reaction. There's two steps to this. The first step, as always, is to form a leaving group slash electrophile. Okay, so that's step number one. And for this reaction, I'll just go ahead and draw it out that we have ourselves an acid chloride group here. There's an oxygen there. There's a Cl, and then there's aluminum trichloride. And this is very similar in this context to the iron. I was thinking about iron and comparing it, and then I drew the iron there. So this is AlCl3. There's an empty orbital there. There's some lone pairs there. Trying to make that look decent. And those lone pairs are going to be attracted to that aluminum. And then the next thing that we get is a very awkward looking chlorine with a positive formal charge and an aluminum trichloride attached to that with a negative formal charge, just like we had whenever we had done the iron reactions. So this right here, though, this is your super, super powerful kick-ass leaving group. This is your leaving group that you're going to want to have for this reaction. And it's so unstable that usually what will happen is this positive charge on a chlorine is so unstable that it's going to remove the bond connecting it to that carbon. And as this comes off, what you get is, you get two things. You get aluminum tetrachloride. That's not really superbly important, still with a negative formal charge. But you get a psyllium ion, or well, it'll be resonance stabilized to form something like this. So what do we have here, though? We have a carbocation. And this, the reason why I'm drawing this out here, I'm just going to give myself some space to show here. Remember that the minor resonance structure is what determines the reactivity of your molecule. So that's my minor, but let's go ahead and draw the major resonance structure. Well, the major resonance structure would be to take this lone pair and satisfy my octet rule, my oxygen, and move it in there. And in doing that, I'm going to have a satisfied octet rule, but I'm going to have an oxygen atom with a positive formal charge. That should freak you out a little bit. So remember, this is what determines the reactivity. Why am I stressing this point? Because when we, this molecule here, this is called, I think, a psyllium ion, I'm not sure. This molecule here is the structure, but this is what determines the reactivity. So let's draw, without, we've already drawn the formation of the leaving group, let's draw the substitution reaction. I just want to clarify that this is our electrophile that we need. Electrophile for this reaction. So let's go ahead and just draw out the substitution reaction. I have a benzene here, an aromatic benzene compound. There's a hydrogen attached to it. I'm going to, it is going to come in and it's going to see this positively charged psyllium ion. It's kind of stable compared to other, but it's still super unstable. And this pi bond is going to attack the carbon. Why does it attack the carbon? Because this is the resonance structure that determines your reactivity. And in doing so, I can't have additional bonds of carbon. I move that lone pair up there to that oxygen. And so what I get with this, and I'll go ahead and just draw my arrows pushing out here, of course, this reaction is the slow step. That's your rate limiting step. Why? Because you've disrupted aromaticity. There. There's a hydrogen there. There's that there. That's your carbocation. But attached to this is a carbon, a lone pair of oxygen there attached to it, and then an R group there. You have a keto group. Those are supposed to be electrons. This pen is a pain in the dick to draw electrons with, but this is that's what you get. So this carbocation that we have here obviously is not going to be stable or stay in that conformation for very long, because we have some type of a conjugate base coming in and deprotonating this, and in doing so we are restoring aromaticity. So this is a very fast reaction, and what we get out of it is, I've drawn these reactions to the ground, man. What we get out of this is, and I'll switch colors to clarify that it's what we added to, is a keto group attached to a benzene ring. Whoa. So that's our final product of this reaction. Alkylation. All right, so with Friedel-Crafts Alkylation, the same thing that we had with before, there's two steps, but I'm going to go ahead and draw the overall reaction. We have an aromatic compound, usually a benzene, with a hydrogen attached to it. We go ahead and put it through some reaction with some products and some reactants, and what we get out of that is a alkyl group attached to it. Now, our alkyl group is usually this, and we run it with conditions of aluminum trichloride. So, let's talk about the two steps. Guess what step number one is? To form a leaving group / electrophile. So, how do we do this? Well, it's leaving group, and in this context, I'm just going to go ahead and draw it like this. It can be any type of an alkyl group that is you can form. There's a chlorine there. I don't know why I drew it with a negative formal charge. It's not negative. There's just a lone pair on that chlorine. And then over here, I'm going to draw aluminum tetrachloride. And I think you can know what happens in these reactions is that the lone pair is going to attach itself to that, or it's going to attack the aluminum trichloride. And what we get out of this is a very goofy looking chlorine having a positive formal charge, aluminum trichloride, and then aluminum having a negative formal charge. So of course this is going to be our really good leaving group that we have already formed. And so it doesn't even stay in this conformation long because you have a positive charge on a halogen. So this sigma bond is going to be broken and in the process pulling itself off. Now, what does this give us though in this reaction? Well, we get ourselves a secondary carbocation floating around, and aluminum tetrachloride still has a negative formal charge. You don't have to use this reaction. If you could as well to form a really good leaving group, you could just as easily use a alkene and then treat that with H2SO4, and whenever you have that reaction there, remove the carbocation intermediate. It's kind of hard to do that because this reaction happens very quickly. In this reaction, this chlorine with a positive formal charge is so unstable that it tends to not happen. But you can do it. Just think of any other ways that you can form. Anytime you form a carbocation, you could isolate. That's what you're doing. So this right here is what we're working with. This right here is our electrophile, and what we're going to do is we're going to use that for a substitution reaction. I'll go ahead and do that in blue for Friedel-Crafts Alkylation. Substitution is the second step. So we have our compound here. It's just a benzene ring being all benzilious. And there's a hydrogen there. And then along comes that secondary carbocation, which I hope you understand that that's really not stable. So there's our secondary carbocation, and this should be familiar to you by this point. Benzene attaches itself, or attacks that positive charge there. And blue. That reaction is very slow because it disrupts aromaticity. And as an intermediate, what we get is a carbocation. And I'm not drawing the resonance structures for each of these, but you should draw the resonance structures for these. So attached to this is that secondary carbocation, and then usually the conjugate base of whatever acidic conditions we're running in. In this context, aluminum tetrachloride will come in. It'll deprotonate it. This reaction will happen very, very fast. I'm just going to draw a downward arrow here to say that it is happening very, very fast. And what you have is you have restored the aromaticity of your molecule. And in getting so, you get yourself a alkyl group attached to your benzene. Reaction, generally speaking, we're only going to be working with is secondary and tertiary carbocations, not allelic ones. And there's also a possibility of having intramolecular Friedel-Crafts alkylations. It's not common, but it does happen.